Welcome, my dear learners, for this course on mechanical vibrations. In this module 2, we are discussing on forced vibration and vibration measuring instruments. So far, we have discussed and derived expressions for forced vibration subjected for harmonic excitation, in which we have derived expression for system response and also amplitude ratio. And also we have derived expression for amplitude ratio during rotating and reciprocating unbalance. And also we have discussed support motion, that is absolute and relative motion, for which we have discussed the expression for amplitude ratio. And also in our previous lecture we have discussed the concept of transmissibility, that is force transmissibility. Moving ahead, in today's lecture I am going to address critical speed. What do you mean by critical speed, why it is important, and what are the expressions for critical speed of shaft? That is the topic of interest in today's lecture. As we all know, if the excitation frequency is equal to natural frequency, then we term the condition as resonance. At resonance, the speed is termed as critical speed. The speed at which resonance occurs is termed as critical speed. Now we all know that at resonance the amplitude of vibration is very high. During resonance, the undesirable forces which are transmitted to the foundation are very high, hence there is a possibility of undesirable failures might occur in the machinery as well as for human life. Hence we want to avoid resonance. So therefore, if we know at what speed resonance occurs, we can avoid that speed and operate the machineries. So therefore, our aim is to determine the critical speed. Once we know the critical speed, we can avoid the using critical speed, by which we can avoid the occurrence of resonance. The speed at which resonance occurs is termed as critical speed. In today's lecture, we are going to derive expression for critical speed of shaft without damping as well as with damping. That is, today's concept is critical speed. Critical speed or whirling speed. Critical speed or whirling speed. As I said, the speed at which resonance occurs, the speed at which resonance occurs is known as critical speed. Now at resonance, the excitation frequency matches with the natural frequency, during which the amplitude of vibration is very high, which is undesirable for machineries. So therefore, by knowing critical speed, I can avoid operating the machinery at critical speed. Now let us derive expressions for critical speed of shaft for two different cases. That is, in case 1, we are going to derive expression for critical speed of shaft, critical speed of shaft without damping. Without damping. What is the expression for critical speed of shaft when there is no damping is case 1. Now in order to analyze the critical speed of shaft without damping, let us consider two conditions. That is, let us have a shaft like this in its undeflected condition, and we have the second condition. Let me use different chalk as the deflected position. This is the deflected position. So we have the shaft at undeflected position and we have the shaft at deflected position. Let us have shaft between the two bearings as shown in the figure. Now let us consider a disc mounted on this shaft. Let us consider a disc mounted on this shaft exactly at the center. Now if I draw an axis of rotation, this is the axis of rotation of this disc which is mounted on this shaft. I have taken the transverse direction also. So now we have the three positions, that is O is the center of the disc when it is in undeflected position. Now we have the new position called C, which is geometric center of the disc, and also we have G, which is nothing but center of gravity of the disc, which is nothing but center of gravity of the disc. Let us say we have G here. Now the distance between the geometric center, and the undeflected position is nothing but deflection, which can be taken as x, and the distance between the geometric center and center of gravity of the disc is taken as eccentricity, which is denoted by E. Now let us consider, let x is equal to deflection which is nothing but distance between O and C. M is equal to mass of the disc which is mounted on the shaft, and we have point C, which is nothing but geometric center of the disc and next we have G, which is nothing but center of gravity of the disc and we have eccentricity E. E is called as eccentricity, which is nothing but distance between the geometric center and center of gravity. It is distance between C and G. Now as you know that since the shaft is rotating, the unbalanced centrifugal force generated by this disc will always act outward. Now it should be balanced by the restoring force. The restoring force will be provided by the stiffness of this shaft. While analysis, we are not considering the self weight of the shaft. Here during the analysis, the self weight of the shaft is neglected and we are considering only the mass of the disc mounted on this shaft. Since this disc and shafts are rotating, this unbalanced centrifugal force which is generated and acting outwards will be balanced by the stiffness of this shaft. So therefore we have one more term called K, which is nothing but stiffness of the shaft. Stiffness of the shaft. Now for equilibrium, what is the condition for equilibrium? Now we have for equilibrium. Now for equilibrium, if I analyze, the centrifugal force acting outward should be balanced by restoring force, correct? Restoring force must be equal to centrifugal force. Now what is the formula for centrifugal force? M omega square R, correct? Now what is the formula for restoring force? Here the restoring is provided by the stiffness of the shaft. The stiffness of the shaft is providing the resistance for the unbalanced centrifugal force. So therefore restoring force is given by stiffness times the deflection. Because I want force, stiffness is defined as force per deflection. Hence the restoring force is stiffness times the deflection, X. This must be equal to centrifugal force. Centrifugal force is generated by the rotating disc, which is given by M omega square r. Here the radius of rotation of the disk should be taken as x plus e. Correct? Now if I simplify, what I am going to get? Kx minus m omega square x is equal to m omega square e. Now what is the formula for x by e? So x times k minus m omega square is equal to m omega square e. That is the ratio of deflection to eccentricity will become m omega square whole divided by k minus m omega square. Let me take m omega square common. If I take m omega square common, what I will get? I will get m omega square divided by m omega square times k by m omega square minus 1. Correct? So I can cancel off these two, m omega square and m omega square. Hence what I can write? X by e is equal to 1 divided by k by m. K by m can be written as omega n square. Correct? That is natural frequency. So omega n by omega whole square minus 1, or what you can write for this? If I multiply and divide by omega n square, this can also be written as x by e is equal to omega by omega n whole square divided by 1 minus omega by omega n whole square. So either I can use this equation or this equation, both are same. Now where is the critical speed? I am telling that the speed at which resonance occurs is known as critical speed. Don't get confused. Students are confusing that the critical speed of shaft is not the maximum speed. The critical speed of shaft is the speed at which resonance occurs. Now where is the critical speed is the question. Now at resonance, what is the condition at resonance? Now at resonance, we know that omega should be equal to omega n. Correct? Now what is the formula for omega n? Omega n is equal to square root of k by m, or we also know that omega n is equal to root of g by delta. Root of g by delta, where g is acceleration due to gravity, acceleration due to gravity, and delta is the static deflection. Delta is the static deflection, square root of g divided by delta. You know that acceleration due to gravity is given by 9.81 meter per second square. Now once I determine the value of omega, that is equal to, once I determine the value of omega n, natural frequency, that must be equal to excitation frequency. Correct? Now what is the formula for excitation frequency? Therefore omega is equal to omega n will become critical speed. Now we know the magnitude. Omega c can be written as what? 2 pi nc by 60 is equal to omega c. Hence I can find what is the critical speed. Omega c into 60 divided by 2 pi. Hence I can find what is the critical speed of shaft. So this is the analysis for critical speed of shaft without damping. Let me pause this video for a while so that you people can copy it down. Later we will derive expression for critical speed of shaft with damping. Now moving ahead for case 2, In case 2, we are interested to determine the expression for critical speed of shaft with damping. Clear? Now the difference between the expression for critical speed of shaft, that is for the ratio of deflection to eccentricity equation for with damping and without damping, is that in case of without damping, all the 3 points, that is O, geometric center C and the center of gravity of the disc G, will lie in the same line, whereas in case of with damping, these 3 will not lie in the same line. That is the difference between with damping and without damping. So therefore, in case of with damping, we have the condition like this: the geometric center and the center of gravity will not lie in the same line. So we have the condition like this. So somewhere here we will be having the geometric center G. Somewhere here we will be having the center of gravity of the disc G. In case of without damping case, all the 3 salient points, that is O, geometric center of the disc C and center of gravity of the disc G, all the 3 will lie in a same line. But in case of with damping, under damping, these 3 will not lie in the same line. These 3 will lie with some inclination, that is inclination with respect to O to G. Inclination with respect to O to G, let us take this as alpha. Whereas inclination between the geometric center and the center of gravity can be taken as phi. Phase difference let us take. And we know that C to G is termed as eccentricity E. And O to G is nothing but what? Radius of rotation R. So this is what we have. Now we know that unbalanced force will be generated at center of gravity of the disc. This we already know. So therefore the unbalanced centrifugal force will be generated at the center of gravity of the disc, which is known to us, which is equal to Fg, which is nothing but m omega square r. Correct? So this will also be at an angle of alpha to the vertical. This angle is also alpha. Now I don't know what is the value of radius of rotation, but I can determine what is the value of deflection of the shaft and also what is the eccentricity. Correct? So therefore, now from the analysis we have, let me consider this properly and write once again only the part of O, C and G, that is position of the disc in undeflected position, geometric center of the disc and center of gravity of the disc. Once again, if I write and resolve the forces acting, that is if I draw the free body diagram again, if I go for free body diagram of disc and shaft, because shaft provides stiffness resistance force, it can be written like this: we have O and we have the deflection X, lateral deflection X. This is the lateral deflection X at a point C, and later we have condition like this. Somewhere here we have G, that is center of gravity of the disc G. Now these angles are known for us. This angle is also alpha and this angle is also alpha. Now the distance between C and G is eccentricity. So connect between C and G, that is eccentricity. Let me connect a line between these two. This is called as E, eccentricity, and this is radius R. Correct? Here we have the force acting, which is m omega square r. Let us call it as force at center of gravity of the disc. Now I can resolve these forces into two components. One is horizontal component and another one is vertical component, right? So if I resolve the vertical component will become what? Fg sin alpha. Now what about the horizontal component? What about the horizontal component of this force? Horizontal component of this force will become Fg sin alpha. Fg sin alpha. Fg sin alpha will become horizontal component, whereas the vertical component will become what? The angle alpha is made with reference to vertical, hence this should be Fg cos alpha. So cos theta is adjacent by hypotenuse. So adjacent is equal to cosine of hypotenuse. Hence this will become cos alpha. The vertical component of force is Fg cos alpha and the horizontal component of force is Fg sin alpha. So I resolved this unbalanced centrifugal force into vertical and horizontal components. Now we have the restoring force for this. We know that the resistance for deflection is provided by stiffness of the shaft. Hence the resistance restoring force is given by what? Restoring force is given by, for the vertical component it is given by stiffness of the shaft times the deflection, that is x. Stiffness of the shaft times the deflection is the vertical restoring force. Now we have the horizontal disturbance also. So therefore horizontal resistance is given by damping force. Horizontal resistance is given by damping force, which is given by damping coefficient times the velocity. What is the formula for maximum velocity? Omega x is the expression for maximum velocity. So now the unbalanced force can be resolved into two components. One is vertical component, another one is horizontal component. We know that the resistance for vertical lateral deflection is provided by the stiffness of the shaft. Hence the vertical resistance is nothing but Kx. And also we have horizontal unbalance, that is Fg sin alpha, for which the resistance is provided by damping force, that is C into x dot velocity. The formula for maximum velocity is omega x, where x is the amplitude of deflection. Now, to determine the expression for the ratio of deflection to eccentricity, one important note we want to do here is that let us take this as phi. Let us take this as angle as phi, and this distance is eccentricity E. E is the distance between C to G, whereas R is the radius of rotation, distance between point O to G. Since we don't know the length R, but I can determine the value of deflection, lateral deflection and eccentricity. So therefore express R in terms of x and E. Express R in terms of x and E. So if I do that, what I will get? If I express R in terms of x and E, so very first thing, express radius of rotation R in terms of lateral deflection x and eccentricity E. Now R cos alpha can be written as what? That is R cos alpha. R cos alpha will give vertical component. R cos alpha can be written as x plus E cos phi. R cos alpha can be written as x plus E cos phi. Now this length is R sin alpha. Similarly, R sin alpha. R sin alpha is this length. R sin alpha can be written as E sin phi. E sin phi. Now I can determine the value of phi, which is the phase difference, using tan phi formula, and also I know the value of x and E. So hence, without using the radius of rotation and alpha, the inclination of the radius with respect to vertical, without knowing these two, I can solve for critical speed of shaft. Now using these two replacements, let us derive expression for x by E ratio. Now for equilibrium we have two cases. for equilibrium. Equating for sum of vertical forces, what I will get? Kx must be equal to Fg cos alpha, correct? First condition, summation of forces acting vertical must be equal to 0. So what does this condition gives? Stiffness times x must be equal to Fg cos alpha. And we have the second condition, sum of horizontal forces must be equal to 0. If I use the second condition, we will get C omega x must be equal to Fg sin alpha. Now use these two conditions and derive expression for phase difference, phase angle phi and the ratio of x by e. That is, using the first condition, what I can write? From first condition I can write that k into x must be equal to Fg cos alpha. Fg is what? M omega square r, correct? Fg is M omega square r cos alpha. Now what I can write for r cos alpha? R cos alpha can be written as x plus e cos phi, correct? Hence k into x is equal to M omega square of x plus e cos phi. X plus e cos phi. Now simplifying further, you are going to get kx minus m omega square x, kx minus m omega square x is equal to m omega square e cos phi. M omega square e cos phi. Take this as equation number 1. So I just rearrange the terms. Now go for second condition. Now if I go for second condition, we have the expression C omega x is equal to m omega square r sin alpha. What is the value of r sin alpha? R sin alpha is equal to E sin phi. So replace r sin alpha by E sin phi. You will get C omega x is equal to m omega square E sin phi. I replaced r sin alpha by E sin phi. Take this as equation number. Now I want to determine the value of the ratio of x by e and also I have to determine the value of phi. So now to find phase angle, that is first one, to find phase angle, you do equation 2 divided by equation 1. So sin phi by cos phi is tan phi, correct? Tan phi will be equal to, what you will get? Tan phi will be equal to C omega x divided by kx minus m omega square x. So I can take throughout kx common. If I take throughout kx common and send it to numerator, I can write C omega x by kx divided by 1 minus m omega square by k. So what I done? I taken kx common and send it to numerator. Now this x and this x will get cancelled. This x and this x will get cancelled. What is the value of C omega by k? Yes, you are correct. C omega by k is 2 zeta omega by omega n, which we have already seen in this module. So C omega by k can be written as C by cc, cc by 2m, 2m by k into omega, correct? Now C by cc is what? C by cc is zeta into omega n into 2 by omega n square into omega. So hence this is nothing but 2 zeta omega by omega n. Hence the value of tan phi is how much? Tan phi is equal to 2 zeta omega by omega n divided by 1 minus omega by omega n square. We got the expression for phase angle phi. Now I want the ratio of x by e. So therefore what I will do, I will square and add these two equations. Squaring and adding equation 1 and 2. Next is squaring and adding equation 1 and equation 2. Square and add equation 1 and 2. If I square and add equation 1 and 2, sin square theta plus cos square theta is 1. So therefore RHS, I will eliminate sin square phi and cos square phi. So I left out with m omega square e whole square. So I left out with m omega square e, m omega square x whole square plus c omega x whole square. Correct? So throughout I will take kx square common. Throughout I will take kx square common. So if I take kx square common, I will take k square x square common. If I take k square x square common, I left out with 1 minus m omega square by k whole square plus c omega by k square. Correct? Yes, this must be equal to m omega square e whole square. Right? So now I can write x square by e square. What I will get for x square by e square? X by e square can be written as m omega square by k square, m omega square by k square whole square divided by this one, right? 1 minus m omega square by k can be written as what? M omega square by k can be written as omega by omega n whole square plus c omega by k is 2 zeta omega by omega n. 2 zeta omega by omega n whole square. So hence finally I will get the expression for x by e. So what I will get for x by e? X by e will become root of this. So square and square root will get cancelled. Denominator I left out with the root. Correct? So finally what is the expression I am going to get? X by e is equal to root of omega by omega n whole square. Square and square root will get cancelled. Denominator I will left out with the root. So hence the final equation will become what? X by e is equal to, so x by e is equal to, the final equation will reduce us to so further simplifying, since I don't have space, I have shown the step and I am erasing it and overwriting that step. With further simplification, I left out with x by e is equal to omega by omega n whole square root of 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square. So this is the final expression. So this is the expression for the ratio of lateral deflection to eccentricity and also the phase difference tan phi. Now here if I determine the value of omega n, or using this equation I can determine whatever is the unknown for me. At resonance omega is equal to omega n, which is nothing but omega c. So omega n can be determined as square root of k by m, or it can also be determined as square root of g by delta, where delta is static deflection. Correct? So and also we can determine the value of omega n as root of k by m, or you can also find omega n as root of g by delta, where delta is static deflection. Square root of g divided by delta, square root of g divided by delta radians per second. Now at resonance we know that omega must be equal to omega n. Omega n is not equal to omega. Omega must be equal to omega n. So omega n numerically I know, this must be equal to omega. Now what is the formula for omega? 2 pi n by 60. So using which I can determine 2 pi nc by 60 is equal to omega n. Find the value of critical speed in RPM. Find the value of critical speed in RPM. So omega is equal to omega n at what? At resonance. So this is the condition at resonance. So using this I can find what is the critical speed. Now if I substitute the condition at resonance, what am I going to get? Put omega by omega n as unity, because at resonance omega is equal to omega n. So if I substitute here as 1, and here also if I substitute as 1, so this will get vanished, right? 1 minus 1 is 0, this will get vanished. This is 1, so 1 divided by 2 zeta. 1 divided by 2 zeta is the value of x by e at resonance. Whereas for without damping, if I don't have damping, what is the value I will get? For without damping zeta is 0. So if I substitute 0, 1 by 0 is infinity. The ratio of x by e will become infinity at resonance. You can see from this equation, or you can substitute the former one which we have derived, that is case 1. From case 1 expression, if I substitute omega by omega n as unity, you can see that x by e is infinity. Whereas here also we can verify that x by e is infinity without damping, that is put zeta is equal to 0, omega by omega n as 1. You can see that here also x by e is equal to infinity. So this is the discussion of critical speed of shaft. That's all from this lecture. Thank you all.